We stopped it on talking about linear programming, and that was only one slide. And then we define continuous, but there was a one term more technical or mathematical we call convex. By the mathematical relationship, if we have a certain reagent bounded by x1 and x2, and then if you give an alpha, the values between 0 and 1, you always can find an x. And this x is varying between x1 and x2 by adjusting alpha. So if you change the value of alpha, you will move x, right? So you all have all the value of x that will be lower than the value combined by this function. And that means you always can have like a shape like that we call convex. And this shape here, of course, is with respect to, if you look at that, is from maybe from this angle, okay? So it's not look from the upper part. If you look from the upper part, it will be concave. So why convex is important? Because of linear programming and many mathematical programming, you can only solve like convex problem. And between these two lines, you can always find the minimum. And then if the problem is concave, then in generalization, we talk about minimization. Then it's very difficult for you to find what is the minimum. So that's why concave problem is much more difficult to solve for many programming. And then you will have another trouble we call local optima, which is also important to understand. The reason was because of if you look at this concave here, the problem is like if you we talk about one problem of using the minus will be you could convert a convex problem into concave problem if you put the minus sign. And then we mentioned that a concave problem is more difficult to solve. And why it's more difficult to solve? The reason was because of if you look at the shape here, let's say that you have the classical gradient-based functions, something you learned probably already in your in your secondary school, no matter in which system you come from. If you learn some calculus, you will know that some of those gradient-based functions will be more like you drive a car and then you move a point to another point. The problem is when you move the point and you find another point, then concave problem will give you this kind of things here will be in the upper part you have no problem because from any point you can go to another point. So you will never have any problem to move from one point and then to another point. So you can move it quite freely, okay? But the problem with like non-convex or concave problem is that you have this problem. That means when you move to here, you already go outside your feasible reagent. And then let's say that if you have something in the here, and then if you have a linear programming, let's say that your linear programming will move a line that is moving a line here. So your line keep moving here. When you put different value, the linear programming, and then you will just stop at this 2 point. Then you will never find something in this middle. So, and then in this part of the problem, it's even called non-continuous. And that's why mathematical programming usually have this limitation, which lead us to talk about how you can avoid this global optimum and local minimum. So of course, if you have a certain reagent, you can find this minimum, but this is only with respect to your reagent. And if you make the reagent larger, then X star here will be the real minimum. So that's why when we talk about local optimum, and in many cases, in real life, it's very difficult to find global because the range might be much bigger. So local optimum is something that we define a certain neighborhood functions. In this case, it's the n here. Now, the interesting thing here will be what happens if you define a reagent, but you still have a lot of multiple slope here. I think this is a classical MATLAB example. This plot is generated from MATLAB. If you key in these functions, so the function by itself is pretty complex, but the decision variable is x and y. So from x and y, you want to find, okay, whether it will be minimum or maximum. So if you drive a car here, the classical gradient-based function, you try to detect the change in the slope. And then let me change back to my laser pointer. If you move your car here, and then when you find that the mathematical functions find that it changed the slope, that is how you do in calculus, then you will trap it here, which is far away from your, now in this case, when we say global, is global with respect to this range that we have the x -3 to +3, and the same range for y. So you miss another optimum there. And that's why one important message why we learn meta-heuristics in the coming part of the lecture. The reason is because of in most of the meta-heuristic method, when they move the point, they use either randomization in order to avoid this calculation of the slope. So you have something called randomization. And then if it is not randomization, then the more advanced algorithm uses some other mathematical approach in order to make sure that we find a new point to move rather than considering anything that is continuous or that is something that we must be convex. And then if you have a meta-heuristic method that are population-based, so this term will be here today, but then on Monday, we will come back to talk more about why population-based is very important for multi-objective. So imagine if you just look at this diagram before we look at the technical details about genetic algorithm. Some of you might have heard about genetic algorithm, but I need to repeat. One very important attribute of genetic algorithm is not about the randomization. It's more about the population. And this is the property of many population-based algorithm. The reason is because of, I mentioned that many methods, you just move from one point to another, you compare the value, you can develop a very simple algorithm in MATLAB in 5 minutes, if I later show you a very simple algorithm. But here, the interesting thing is all the population-based algorithm, they will more likely put a net onto your search space. So when we use the term search space here, we, of course, the z-axis is not belong to the search space, but the color that you see here, the range, the search space is constantly of the range of x and y. That means -3 to 3, that is the range of x. And then you times the range of your y and give you mathematically called it the search space. And then now we just have a one set. So instead of we call it space, it's more like a line. So you have an objective line here. But later, when we talk about multi-objective, then the term objective space may be more relevant. Now, genetic algorithm will, together with other population-based algorithm, will more or less throw a net onto your search space. And the good thing there will be, that means that you try to collect more samples from your search space instead of just like a car moving from one point to another. And that is a very important aspect to understand before we move on to talk about genetic algorithm. We touch a little bit upon linear programming, and then the problem needs to be convex, continuous, and then it's easier to solve. So whenever you can formulate your problem into linear programming. So do that because that will be readily to be solved. And then if the problem is non-linear, and then you're also looking at the global, and then you not only you don't have some exact mathematical calculation, but you can only approximate. Like simulation, you always just have approximations. So this group, no matter you call simulation based or non-simulation based, it belongs to the meta-heuristics. So you could find that meta-heuristic. First of all, it can both solve both computatorial or continuous problem. And then you also can address a global or local optimum problem. And then here you also see that it's also contact to nonlinear and approximate model like simulation. Before we continue to talk about, I think I have some problem with the slide. I think Yeah, I think it's good to go through a very simple example to talk about integer variable. And then in my topic covered, I mentioned that before you consider to use optimizations. So if your problem fall into a short list of variable, you have only a few variable you want to test, then maybe you should avoid all of them altogether. And one simple method that you can use to study your problem, which avoid optimization, is called the design experiment. Let's look at the simple, and this problem is not new already. I got it from this paper by some researcher from Israel. And the model they call is called a G max width. They talk about that max width can be regulated. If you have heard Matthias talk about the calm width principle, that you bound your system with a constant work in process in order to limit your work in process in a production line, or you can even do it for supply chain. Then this paper, the contributor talk about you can regulate the inter-arrival time to further improve the performance. And in this experiment, I tried to do some very interesting things. I put this as a bottleneck. And if I call this a bottleneck, there's a reason. We will talk a lot about bottleneck next Thursday, but today, just bear with me to understand here, we set the processing time to be longer. So in industry, they call this a cycle time bottleneck. Especially, I hear people in Sweden, when they talk about bottleneck, what they mean is actually they call cycle time bottleneck. That means the processing time of the machine is bigger. Now we want to do an experiment, not necessarily in optimization, but it can be also optimized to performance. We have 4 to 5 factors. Let me see. I just have 4. Factor number 1, according to Gmax width, we have the inter-arrival time, that we have a high level and low level. And we also test with a high level and low level work in process. And then normally in the industry, they understand that before the bottleneck, they need to have a larger buffer. But in this experiment, I add one more factor into the design experiment, and also try to test the size of the buffer behind after the bottleneck in downstream. Let us look at the result you get from facts if you run a design experiment, full factorial, and then we normally use this notation to represent how many simulations you need to run for a full factorial. How many factors do we have? Now we have 4 factors, and that's why it's 2 to the power of 4. And you can imagine if you are testing 2 levels, a low level and high level. We have a lower level buffer 1 and a high level with 10, and then calm width level will be 5 to 50 from low to high. And then according to Gmax width, we test between inter-arrival time of the product between 200 and 400. So these are 2 levels. And if we have 2 levels, then we put a 2 here. Then of course, it's possible for you to set multiple levels. Let's say that you have 3, but suddenly you will have this number become 3 here. So we will come back to talk about these notations to decide how many runs we need when we talk about bottleneck analysis. But it's not difficult to see that the result, if I try to highlight for you here, you will see that which one will give you the highest throughput. I think very quickly you can see that this is the highest throughput, and it is quite expected that the inter-arrival time will be low, and then calm width will be high, and then you have high buffer before and after. And the interesting information is if you compare with another setting, which you have only one small difference, you will see that are quite contrary to people understanding industry is if you have a cycle time problem, cycle time bottleneck, then you find that it's not only the buffer in front of the upstream of the bottleneck station that is important. You find that there is a quite significant difference. But then, of course, in this case, if we only bother about the throughput, then of course we have a single objective. So you find a peak there. But then you will find that it's also interesting to notice another thing that is a bit puzzling. And that is the cycle time actually is not increased that much, but actually is reducing, and is even statistically significant if you look at this number. So this solutions, number 8 here, is actually both good in throughput and also good in cycle time, quite contrary to our factory physics knowledge compared to the previous solutions. And then with design experiment, you could do a lot of things more if you export your result from, let's say, facts. You copy the output table, like what I showed this output table in the previous slide, and then we can move it to Minitab, or you can also do MATLAB. More demanding will be you can also do something in Python, but the Minitab is the easiest and maybe handy for you to make this a cube plot so that you can compare 4 variables. So imagine now we have just 4 variables that we need to compare and decide. We need to so-called optimize. You will end up with more questions or cannot be visualized so easily if you have more than 4 variables. In this case, we already need to use a 2-keep because we have 4 variables. The keep gives you a good visualization for 3 variables. But another thing that I really like nowadays, the Six Sigma is not as popular as 10 or 20 years ago. At least I don't think in your education you cover too much about Six Sigma. But in Six Sigma, especially when people use Minitab, there is one method called a Pareto chart. Later, when we talk about multi-object optimization, we have something called a Pareto frontier. In here, this is something quite different, even though the name Pareto is still the same. How many of you know about this name, Pareto? I don't know if you have background in industrial economics. Okay, so okay, you talk about Pareto diagram. Yes, okay. So this Pareto, the name is, I think if pronounced it correctly, is Rivera Pareto, is an Italian economist around the First World War time. And the most famous of his theory is actually not Pareto front or Pareto chart that we use his name here. It's a theory called the 80-20. So 80% of your profit coming from 20% of your customers. You may also say that 80% of your trouble coming from 20% of your relatives. Or you can also say that maybe your happiness also coming from 20% of your friends, and so on and so on. So in real life, you have this 80-20, but then the world economy is already in a shape that we may not even talk about 80-20. It's not only 20% of the people that own 80% of the wealth in the world. I think we are now talking about 1 to 99. So his rule is now even more extreme compared to what he studied in around World War I. But this Pareto chart here will give us some interesting information that you would like to look for whenever you're doing study of your problem. Is not only telling you which factors, in this case, we know that factor B, the convex, is most important. So B is, I'm sorry that if it's too small, but let me just zoom a little bit for you so that we can be closer here. You could see that B is about the max width, and C is the first buffer. But there is a very interesting thing that we need to observe. It's there is something called interactions. In very simple terms, interactions means that one factor plus another factor will give you, in Sweden, you call it catch-up effect. This is not really a good English term, but I like to say that 1 plus 1 equal to 3. That is a positive interactions. And B to C together, they give you some positive interaction. Later, we will analyze even deeper about why. Okay, but we expect, remember, we talked about inter-arrival time, suggested by those researchers in Israel. But my research or the experiment I did actually show that A actually is not very important. I think even A, B, and A, I think A always need to connect to other variable. So it seems to me that from this simple experiment that their theory that regulating the inter-arrival time doesn't really matter that much compared to the convict level. The convict level is very significant, no doubt. And then we know that the buffer before the bottleneck is also important. But then we find out that there is the interaction between the convict level and the buffer level. But then you also need to consider the buffer afterward. And for a few factors, in more advanced data mining and data analytics, you may have used or seen something called the scatter plot. The principle is very similar, but in that case, you have more data points coming from your data. But from design experiment, those data points are not coming from the database, it's more from the simulation. And in this case, we have two levels. And with two levels that we can do this so-called interaction plot. The interesting analyze here would be the Pareto chart already told us there is a certain interaction between what do you remember? Between the mark script and also the first buffer, the buffer before the bottleneck, right? You could see that what we call the positive interactions, or in Sweden, you like to call catch-up effect, is when both of the value are high convict and high buffer capacity, then this line is not parallel. So if the lines are parallel, that means their interaction are actually not very strong. And surprisingly, even though we find something in the Pareto chart, we find that the line are pretty parallel. And if you find the line are pretty parallel, then it actually tells you that it doesn't really help that much in having the positive interactions. And then when we talk about positive interactions, you should also remember that it is very possible, let's say that. Now you don't find that in this example, but it's really possible that you find something like that. And then that would be something you call negative interactions. Negative interactions means that you're not getting 1 + 1 = 3. You are getting 1 + 1 = -1. And this can happen when you combine several factors together. Now, before we go for materialistics, the things I want to tell you here is by studying this design experiment, you understand quite much things that is not normally you can do it in the optimization. So in optimization, you get the solutions, but sometimes not only getting the solutions, you also want to understand better about the relationship of the factors. We move on to talk about simulation-based optimizations. So we still have like 20 minutes, and then we can cover quite much about simulation-based optimization. Now, we have seen linear programming. You put your objective, that will be the profit. And in this case, it's utilizations, okay? And then through linear programming, you get an optimal solution. So mathematical programming, they are real optimization too. But when you use simulations, they need to be careful because simulation belong to something we call iterative model. And then these two figures tell you very clearly the difference. In industry, or maybe before you first start to use a simulation, you may say that, oh, I want to use simulation because I want to optimize the system. But the truth is, the simulation and optimization, there are two different things. The reason was because unlike linear programming, you give the design, let's say the number of machines, the number of products you want to make, like the case in the linear programming problem that we have seen. Now you put it into your model, and the model will give you something called performance measures. In this example, we show utilization because we want to contrast in the objective there. But in the previous linear programming problem, and later you see some other example, will be about profit, will be about throughput. It will only give you the performance measures. And then if you are not satisfied with the output, what do? You go back, you come back here, you change your design, you make the iterations, and then you get the new value. And then if you are not satisfied, you go back. Okay. So who is doing the optimization functions? So it's not the simulation, right? It's you, the user, the decision maker, the analyst. You are the one that made the change, and also you are the one that we call optimizer. So simulation is not alone in terms of a iterative model. In my lecture, if I give you this lecture about factory physics, I will cover this model. But in here, this year, I don't know if Matthias have mentioned about this slide anyway, but okay, I'm sorry, I make the wrong click here. This is called the Kingman's equations, or sometimes we just call it VUT. V means variability, U means utilizations, and then T is the processing time, okay? I don't know if Matthias mentioned something about the relationship with the waiting time in the queue and then how busy your machines. But one term that I always need to tell is very interesting, is utilization is not the same thing as availability. You have learned something about availability in some other lectures with Matthias using my slide there. But utilizations is an output. That means how much the machine is occupied. In a hospital, it means how much the nurse and the doctors, they are occupied. And then if they are occupied by 100%, then the value will be 1, because the utilization here is between 0 to 1, meaning that 0% to 100%. The interesting question is, by this Kingman's equations, do you think that you can have the utilization to be 100%? So that is a very important theory principle in factory physics, is if you have the utilization, no matter you talk about a nurse, a doctor, a machine, a worker, if you approach 100% occupations, utilizations, then in theory, the waiting time will be infinitely long. This is what the Kingman equation tell you. But anyway, for this part of the lecture, what I'm trying to tell you is if you want to use a Kingman's model, this is a mathematical model. This is not a simulation model. And this is not a linear programming model either, but this is a queuing model, okay? In queuing theory, you can set the number of machines, number of servers to be m. And when you increase m, you will drop the waiting time. And that is a very simple principle. When you increase the parallel number of servers, number of workers, machines in a certain workstation, then you will reduce the cycle time. But the question is how many you need to allocate in order to get a cycle time that you satisfy, in order to minimize your cycle time. So what you do is to have something that changes the m. If not manually, then you need to have a mathematical algorithm. And that's why simulation is not alone. Simulation and many other methods, they are also belong to iterative model. So when we call simulation-based optimization, the principle is simple enough to tell, but then quite complex to develop in terms of in both sides. Okay, I will tell you more details later. But this slide could give you a lot of information about simulation-based optimization. And then it's always important to, whenever I come to this slide, it's very important to put a red line here. The reason is because of, as I mentioned, to both sides, they see each other as a black box. So the optimization algorithm, it only see what? The decision variable, x1 to xn. And then if you have one objective, y, then you have one y, but you have multiple objectives. You have y1 to ym. So is this exchange a clear protocol exchanging between your optimization algorithm and your simulation model, who make something we call simulation-based optimization? So I keep mentioning already in the early part of this lecture, already talk about, I can go to the very last part already. Is there no guarantee that it's a fast method, and it's also pretty dependent on your computing power. I don't think many of you know that you can run parallel simulations with facts. So if you don't know that, when I give you the demo now, most likely on Monday, then I will show you some trick how you can make some parallel simulation run. But actually, it's well possible that you can make a facts model to run on the cloud in some computer clusters. But it's very dependent on your computing power. But the good thing is somehow is based on a combination of artificial intelligence. We will talk more about neural network in my next course, but in this course later today, then we will see more about genetic algorithm. So normally is a mixture of some some artificial intelligence algorithm. So it belongs to this type of method to make it automatic. So the important thing to understand here is there's no guarantee that this loop is faster than manual method. But this loop that is running like what I tried to illustrate here is that this loop will be automatic. So you don't need to be there in order to keep watching, but then the optimization will drive the simulation to test many different results. But today, I think many of those artificial intelligence methods, they actually work in this way. And then for very high-end reinforcement learning and deep learning, that the very typical example is AlphaGo, the optimization algorithm, the artificial intelligence algorithm that beats the Go player. They actually is like playing with the game like millions and millions of the time. And in this case, now we are not playing a game, but we run the model, hopefully not millions of times. Even though I work with optimization, the simulation-based optimization for 20 years, I don't think I have ever run any model for millions of times, unless it's a very, very simple function. Otherwise, you already need to wait for some hours in order to get your result when your model is moderately complex. And that's why millions of run, I think, is very time consuming. We have a list of variable here closer to what we have in productions and even supply chain. So X can be the buffer size, batch size, number of machines, can be more complex like word sequences. And when we come to bottleneck analysis, we will add this lean improvement. And then the output, we will cover more later. But typically, in your earlier educations, you talk about throughput, work in process, lead time. They are typical. And I hope that materials also cover a little bit about the surface level. If no, then I think when I come to another slide to talk about the surface level in the multi-objective, we will go have more detailed discussions. If your y is one single objective, is your y is bigger than one, then normally we call multi-objective. But nowadays, when people solve a problem that have an objective more than three, then we call many objective optimizations. I will not cover anything about many objective in this course, but in the next course about prescriptive analytics, then I will have one lecture to talk about many objective optimization, using some new result from Professor Depp, for example. We can almost stop here by giving you a quick overview of an example, which you can find in Facts Analyzer. I didn't really well prepare for this one. Let me see if my facts really working. I have many other versions of Facts Analyzer. So let me see if this one working here. I think it's good to give you a demo before you leave today. So this is facts. And then we are going to make this model, not together, but I have something like a good cooking course. I have already a ready model. And then this is a ready model I want to show. The model looks to be complex, and it's actually a little bit stupid. I will tell you why, but this is something I can show you here. Okay, now the problem we got from Winter Simulation Conference from Alvin Loy is a very well-known name in simulation statistics, and McComas 2002, so pretty old paper now. But they illustrate a simple example, and they compare the performance of several algorithms, including OpQuest and in Arena, and also I don't remember which software. I'm quite sure Arena and OpQuest. The problem formulation was like that. You have 4 workstations. Your decision is to decide the number of machines in each workstation. So in factory physics term, workstations and machine, they are different things. Workstations are holder of multiple machines. So you can have a multiple machine, multiple server in each workstation. So your decision will be M1 to M4. But of course, you're not going to have a infinite number of machines because they will cost you money, 25,000 per machine. So you have a constraint here. And then you have the buffer constraint because your next decision will be the buffer between so-called interstation buffers, buffer 2 to 4. So we denote that by B2 to B4. So in this problem, we have 2 good constraints in order not try to limit the search space there. And we solve it into a single objective. And then we put this profit functions, the throughput times you earn 200 per product over a period of time. Your machine will cost you this amount of money and your buffer will cost you $1,000 each. So this is the basic information about the problem. And then we have the objective. So good. Now we are not in the Alice in the Wonderland situation. So we have the objective. We know we want to maximize the profit. But we also need to make another level of decision apart from the constraint. Good, we have the constraint. But then another thing is related will be the range of the variable. So in this example, we follow in that paper, we choose the number of machine in each of those machine workstation will be 1 to 7, 1 to 7. And then the range of the buffer for each buffer will be 1 to 10. And then the number of options together, this is not a correct one because of if you consider how many combinations, even though they looks to be not many, 1 to 7, 1 to 7. But to consider how many possible configurations, this number can be very big if you have a 7 times 7 times 7. But remember, this is not a correct description of the search space. Why? Because you have the constraint, right? So that means you will know that already from now, if you test a buffer that have a 10, 10, 10 there, is already validate the constraint. So the optimization shouldn't test the solutions that is already outside the bound of the constraint. Now let's look at the model. I think before we go today, I think now I show you a more stupid model because of we use a max sweep to make the bound, and then you see that the bound of the, sorry, I think we use the max sweep in order to decide the number of stations. So this is an old model, but then if I want to show you that a new model that we do will be using the parallel machine. So if we convert it into parallel machine, then the decision variable you want to change will be this number of operations or number of processes. So this is the parallel operations. And then for this demo, I can tell you that you can start to have a look on chapter 7 and maybe also play with chapter 8 a little bit. If you really complete the chapter 6 in your handbook, will be to click and edit optimizations. By the end of chapter 6, you already start to use some design experiment. And that's why I mentioned about food tutorial design. Another very common method is called the Latin hypercube sampling. I'm sorry that this part I cannot zoom, but hopefully you can still see what I'm pointing there. This tube belongs to the design experiment. I showed that earlier in this lecture. But let's say that we want to use some optimization. And for single objective, I can recommend differential evolution, PSO, or the best one in my knowledge will be CMAES. But for single objective, we can try some of them. But for this demo, before we leave today, I just want to tell you that when we decide the decision variable, the principle is like that. Let me delete everything here in the input variable. Then when we add the input, we choose the decision variable by graphically clicking, let's say that the pair of machines, we mentioned that we want to try the number of operations. If you click the number of processors, it will show a default value. We allow people to do something called a multiple choice. It was developed by one of my PhD students, graduated 2018, called the multiple choice method. What multiple choice means is that you can add multiple range here, which is very interesting. Imagine if you have a discontinuous search space, then this multiple range will be very interesting. For production logistic problem, I think it's not very easy to visualize, but when I work with automation and robotics, they imagine that your robot is okay to move in a certain range, but that it should avoid another range. So the range of the robot moving in the X, Y, Z plane needs to be limited by certain multiple range, and this multiple choice set will be interesting. But if we make it simpler, we take away this default value, we test 1 to 7, and then we forget about this optional. If we want it to be test 1 to 7, and we put a plus there. Okay, by doing so, we already have made something that is made it more difficult for many algorithms, especially you want to develop yourself. First of all, it consider an integer. So you see this variable is the integer. And then we have a range there. And if it's an integer, that means the optimization will test 1, 2, 3, and so on. So your search space will become discrete. And for some method, it will be problematic, but for materialistic that we're going to use, then it's not the major problem. Now, we can use something called add input, parallel operations, and then we repeat similar step, 1 to 7. Now, if I do that, it will try to check all the parallel operations here, and then make them equally with the decision variable. And then we can do it for the buffer. And for the buffer, we want to test the capacity is 1 to 10, according to Law and McComas paper. So here is how we set up the optimization problem. And then, of course, the formula is more complex because of here. We come throughput, not how many you produced it, the cost of the number of operations, and then the cost of the buffer. We put it into one objective called a profit. Now, this is not an exercise in your handbook, but this information are given there in the chapter 7. So today, if you say that, oh, you're interested to test a little bit about what I have done, you can go back and then find this information in chapter 7. But this is not a homework. So if you don't want to do that, this is okay. But I just give you more information about if I make the demo here, and then finally, remember we have the two constraints defined in McComas paper, Law and McComas paper. So I make you a very simple demo. If you really like, you can try yourself. The model looks to be very simple. This is exactly the same model you will find in chapter 7. Okay, now actually it's already past 12 o'clock. Before I think I stop recording, anyone want to ask me some questions?